You may have seen now that we are drawing linear models, but sometimes linear models can be a little bit frustrating to work with because they're somewhat limited. Take this data set on the left. The data set on the left is definitely separable. We'd like to be able to draw a hypothesis like the one on the right. But with linear classifiers, we simply can't do that. We're restricted to hyperplanes that can only cut off a part of the boundary. So we could draw a classification boundary like this, or even like this one, or maybe even like this one. But we're not going to be able to get all of the points right. We have to go beyond having just a linear hyperplane that's going to be able to get the hypothesis right in this case. But can we do that with a linear model? The short answer is no. But we can appeal to nonlinear mappings to get a boundary that looks like the one on the right side. Let's look at another example. Here we're examining how much credit to assign a customer given the number of years of residence, xi. This is just a univariate case. So let's introduce some notation first. Let's say that the square brackets here means that whatever is inside is going to be a 1 when it's true or 0 otherwise. We're just going to say that the period of time between 1 year in residence and 5 years of residence is more significant. We can see this by thinking of this on a graph. Okay, so if we have some time t, which takes the values of xi, we can say that the time of residence being less than 1 year is generally regarded as unstable, right? And the period beyond 5 years, so whether you've lived in your residence for 5 years, 10 years, or 15 years, we're generally going to think of this as a stable time period. Okay, and where xi really takes to matter for the problem of determining the amount of credit is when we have this time between 1 to 5 years. So this is going to take off and become much more significant. So looking at this, you can see this graph is showing that xi affects the credit line, but in not a linear way. So we can think of this as being a higher credit line that we'd like to improve on the y-axis. And in short, we can't do that with a linear model. So we're going to have to appeal to a nonlinear mapping of this single variable to try to capture that. So all three different types of linear classifiers that we're going to go over, including the perceptron, implement a linear function of the signal. The signal is just basically this portion, right? Theta I times xi, right? Which when we expand out in linear regression means that we have a bias term, x0 equals 1, okay? And all of the other terms here are just multiplied by a weight coefficient that we're trying to determine. So this is a linear signal because we are just taking the sum of the individual products. And for linear classification, we don't take the signal as is, but we take the sign of the signal, whether it's +1 or -1 here, right? Above or below 0. Now, all these algorithms work because of the linearity of the weights. For example, the linearity of these weights here in red. But we don't say anything about what form xi all of these x's can take. They could be anything. The fact that the raw observations could be one form, but it doesn't mean that we're limited to that. So then there's a very interesting trick. We can take the raw observations that we have in the feature vector and transform them any way we'd like. And the way we do that is to denote it using phi, any transformation function. So for example, in this case where you can see on the left, we could take all of the blue dots and you can see they're close to the origin here. So we could use, let's say, some type of classification where we could just draw a circle around these. What we can do is transform them by taking all of the different raw observations and square them, right? When we do that, we're going to be able to end up with a transformed observation that puts all of the data points close to the origin. When we do that, we can draw the same type of circle classifier in a different region like this. So it's important to see here any type of transformation that we could use, whether to subtract, add, multiply, or take exponents of the raw data values is fine. What we're going to end up with is a transformed space, we're going to call that Z, that's going to preserve the linearity of the classifier because the linearity is in the weights, not the observations. Okay, then let's take a look at how this is going to work overall. I'm going to start with the original data in its own X space. So we have some samples from all of the possible observations X. Next, using the phi function, we're going to transform the data. We're not going to say how we're going to get this transformation function yet, okay? But once we do this transformation function, we're going to end up with the observations, the same observations, but transformed. So we're going to take all of the different xi's and transform it into a zi. The zi's are going to live in their own space, which is just a transformation of all of the x's. Next, we're going to do the linear classification in this transform space, right? So we're going to either take something like a binary classifier, such as the perceptron, and look at the sign between the signal, which are the weights that we've determined in this z space, and separate the points positive from the negative ones. So we're going to come up with a hypothesis that's in the z space. And finally, we can take those classifications and move them back to the original X space. So let's recap what transforms to what. We're going to start with our observations. Right, when we have the data points consisting of a number of dimensions, we're going to use the phi function to transform them into the z space. The z space may have a different number of dimensions as we've denoted by this n tilde. What about the individual set of examples? Well, that's pretty easy. For each of the individual instances, we're just going to transform each of them using the phi function. So we're going to end up with the same number of examples overall, or m examples. What about their labels? We actually don't have to do any transformation using phi for that, right? They're going to maintain the same labels as they would in the original X space because we're not transforming the labels. We're just transforming the coordinates of the inputs. How about the weights, theta? How do they transform? In fact, we don't get any weights in the X space because we're not classifying them as a linear classifier in the X space. We're actually only doing the classification in the Z space. So this is why we've denoted it with a tilde. We're going to get a different number, possibly, of features as denoted by n tilde, which is going to say that when we do the transformation, we can either change the number of dimensions to be a larger amount or a smaller amount. And so our classification is going to be this h tilde theta of x, which is just going to be using in the linear classification case, or binary classification, just a sign of the transformed data point in z space times the weight vector that we have determined for it. Right? As we've seen here, it's basically the same. Just that we're saying that z is basically a transformation of x through the phi function. Here, let's go to the learning diagram and summarize. We have an unknown target function that we'd like to try to make sense of, our f of x. And we're going to see examples of that through the training set that we're given, which are representatives of true cases of f of x. We're going to use a learning algorithm here, a linear classifier that has constrained to a certain hypothesis of just hyperplanes. And we're going to induce a final hypothesis of h theta, which is as close as possible to f. So what we've done is we've used a nonlinear transformation to change our x's into a z-space and then apply the classification on the z-space. So we could transform, for example, all of the x coordinates, for example, in a two-dimensional case, our x and y's could be x1 and x2, and just square them to put them on a different axes, right? And this would correspond to the first view graph that we saw earlier, which allows us to classify them on the closer to the origin.
So I'm sure many of you, after watching this segment, have the same burning question, which is, that's great that we have nonlinear transformations and all, but how do I pick the right nonlinear transformation to use for my problem? Is there an algorithm that I can use that will help me pick the right nonlinear transformation? And unfortunately, the short answer to that is no. Our job as machine learning engineers and data scientists is to go through the raw observations or features and try to pick out the right information to provide the machine learning classifier so it can weight it appropriately. Of course, in the last couple of years, we've seen the rise of neural network architectures, which we'll study later in the semester, which have a semblance of the ability to pick out the right nonlinear transformation of the features through multiple hidden layers in the neural network architectures. It's a very exciting part of machine learning that we'll be covering very soon.